Okay, what am I going to ask? Now, what are the 4 conditions required for a deadlock? Or how does a deadlock happen? How does a deadlock take place? When all 4 conditions happen. What are those 4 conditions? Name one of them. Okay, non-preemption. Right. Who would give me another condition? All right. Another condition? Say again?
Circular weighting.
Okay. Circular weight, non-preemption, and mutual exclusion, and hold and wait. So those are the 4 conditions required for a deadlock. How do we prevent a deadlock from happening? Yeah? Thank you. The question wasn't for you, but yes, thank you for the answer. If we can remove one of those 4 conditions, then the deadlock will not happen. So that's how to prevent a deadlock. If you're asked, how do we prevent a deadlock? By getting rid of at least one of the 4 conditions. If we can remove one of those 4 conditions, then we will never have a deadlock. Right. How do we avoid a deadlock? Not prevent it, avoid it. Okay, anybody? How do we avoid a deadlock? Avoiding a deadlock is by using Banker's algorithm. Thank you. And the idea of Banker's algorithm is to keep the system in a safe state. That's the main idea. Keep the system in a safe state. And the system may move into unsafe state if somebody requests some resources. But before we agree, give them the resource, we think first. If we give the resource, is our system going to change and move into unsafe state? If it is, then we'll refuse. We will not satisfy the request. We'll say wait. And we get other requests until we get a request that will not cause our system to go into unsafe state. Okay. Have a look at how, if you need to explain Banker's algorithm, how is it explained? Right, what else did we, how do we detect a deadlock? How do we know there is a deadlock in the system or there is not? Any idea how deadlock is detected? Anybody? How do we find out whether there is a deadlock? Remember, you could have 50 processes in the system. They're all running. Well, running, some of them at the CPU. Only one would be running at the CPU. The others are printing at a printer or a scanner or reading from some input device or writing to a file. They're all busy, even though the processes, while they're using the IOs, they're asleep. They're in a waiting state. So only one process really is executing out of those 50. But all the others that are waiting, there might be 4 or 5 of them, they are waiting in a deadlock. They never come out of that wait. But the rest of them, they're waiting, but they come out of a deadlock when the waiting, whatever they're waiting for is over. So when one process is waiting for a printer to print a page, once that page is printed, then the process will be moved. It's not waiting forever. But sometimes you get 2 or 3 or more processes that they are deadlocked in a waiting state. And that's not really a great thing, and that's the deadlock. But how do we know which of those processes are deadlocked and which of those processes are waiting but they're not in a deadlock? No, they're all kind of wait, they're asleep. You don't know the printer is printing for which one of them. Okay, yeah? Okay, how do we know there is circular weight? Okay, usually we need to draw a diagram where there is, the technique is the resource allocation diagram. that will look at all the processes, look what they need and what they've asked for and what they're waiting for, and then you'll be able to identify whether there is a deadlock or not. We looked at those diagrams, and you need to be able to check them. We'll have another look again at few diagrams and see whether they're in deadlock situation or not. And then if we identify which processes, 3 or 4 of them are deadlocked, they never come out of that deadlock. That's the problem with deadlock. Processes that are deadlocked, that they are actually locking each other, they'll never come out of that deadlock. Not unless something from outside. But those processes, they're all asleep and they never come out of that sleep or that wait until some outside interference happens. And that's where we come in, and that's where the next point is for us to know how do we recover from a deadlock. So if we get few processes are deadlocked, maybe in a system there are 50 processes running, 5 of them are deadlocked, the other 45 are all waiting, except one of them that's with the CPU is running, but the others are waiting for a printer, like there's something's being done on their behalf, and they're not deadlocked, but they are all waiting. And it's for us to identify which ones are waiting and they never come out of that wait. That's the deadlocked one. We've done that with the diagram, with the resource allocation diagram. But once we identify them, we know there are some processes that are deadlocked. How are we going to get out of that deadlock? And that's called deadlock recovery. So we've looked at how a deadlock happens, what is required for a deadlock to happen, those 4 conditions, and how do we prevent a deadlock by removing 1 or 2 or more of those conditions? It's not always possible. A lot of the times it's difficult to remove the conditions. And we looked at detecting a deadlock. How do we know there is a deadlock? And now we're going to look at how do we recover from a deadlock. So identify how does a deadlock happen, how do we prevent it, how do we avoid it, and how to recover from it. And you could be asked any of those questions. So I'm going to just ask the other question now back again to how does a deadlock happen, and then how do we prevent it. To prevent it is to remove one of those 4 conditions. How do we remove a condition? How do we say, right, first condition is mutual exclusion. First, what does mutual exclusion mean? Or non-shareable devices. How do we make a device that's normally a dedicated device that can never be shared? How can we make it shareable device? Any idea? And that's called turning it into a virtual device. So that's the definition of a virtual device. If you're asked what's a virtual device, it's a device that normally it's dedicated, but we use it as if it was shareable, as if we cannot turn it into a shareable. The printer is dedicated. We can never change it into a shareable, but we change it into a virtual device, which means we know it's dedicated, but we'll use it through somehow, some idea or some trick or some mechanism that we make it appear as if it's shareable. So we call it virtual device, okay? So virtual device, don't say a virtual device is a shareable device. It's not. It's still a dedicated device, but we use it in our system as if it's shareable. But that's why we call it virtual. Virtually shareable, that means almost shareable, but it's not real. Just like when you say virtual reality, it's not reality. It's something that mimics reality, close to reality, but it's not real reality. Same with the virtual shareable device. It's not really shareable. It is still, the printer can only print a job of one, the work from one job. But we make it to the jobs feel like it's shareable. How do we do that? Anybody knows how can we turn a dedicated device into virtual device? What did you say? Spooling? Yeah, so spooling. Anybody knows what's the idea of spooling? If you're asked to explain or describe spooling? Anybody knows how to explain it in a couple of statements? Yeah? Yeah, give it a go. All right. Right. So spooling is actually when a request comes from a printer, we don't let it go straight to the printer. When a process wants to print, it sends a request to the printer. No. We have a little program, we call it the spooler, small function, that takes it from the process and doesn't send it straight to the printer. It saves it in memory, in buffer, or on a hard disk. And gets another request, it takes it from the process and saves it in memory and say, yeah, we've already printed it. It may not have been printed. It's still in memory. And it keeps getting lots of requests. That's why it's virtual. So every process thinks, whoa, two processes send print request at the same time. And the spooler will say, yeah, we've done yours. It's all done. When in reality, it's not done. They're just in memory. But normally, a process sends a request to the printer and sits and waits for the printer. Printer's really, really slow. Wait for a few seconds, you're wasting time. Things work at the speed of light inside, almost the speed of light. But they have to wait for a few seconds. They can go to the moon and back in a few seconds. Right? So spooling, you get processes send their requests, but the requests go to a spooler, a program that saves their output in memory and say, yes, it's done. And then it starts sending one at a time to the printer. But processes, they don't have to wait. Sometimes a process finishes completely and leaves the system, and its output has not even been printed yet, but it's on the queue to be printed. So that's why we say the printer now is a virtual device. That's almost shareable. It appears to the processes like it's a shareable device. Three of them can send at the same time jobs to the printer, and they get almost a response immediately and say, we printed your work, when it wasn't printed yet. But we'll print it later. So that's the idea of spooling, if you're asked to describe spooling. There are a number of things. So first, there are 4 conditions in order for a deadlock to happen. How does a deadlock happen? We need 4 conditions. And they are mutual exclusion devices, non-preemptive, hold and wait. What's the other one? Thank you. And circular wait. So how do we get rid of mutual exclusion? Is by spooling. And spooling is processes, process 1, process 2, process 3. Usually, there's a printer, and if they need a request, they have to send it to the printer. If the printer is busy, they have to wait in a queue. They're waiting. So this process sends a request, might have to wait for 5 minutes or an hour, depending on how long will this one take to print the one before, and its own job as well. So instead, we say, don't go straight to the printer. We have a small spooler. That's a program, small process that will take all the requests and put them in memory. So here's memory, main memory, and puts the job here. That's printing request to process 1, process 2. All the printing is saved here on process 3. Or it could be on the hard disk. Some use a hard disk as a spooler or as a storage space, and some use main memory. But once we get the requested material to be printed is saved here, you can tell the process, yeah, it's done, it's printed, but it's not really printed. So that process can go, doesn't have to wait. They'll all go and their jobs are here. And then the spooler will send each one of those jobs to the printer. But the processes are not waiting on it anymore. So that's how we get rid of mutual exclusion or dedicated devices. How do we solve the problem? An example of how a dedicated device can be turned into virtual device. So if we can do that to all our devices, then we'll never have a deadlock. But that's not the case. We can't do it to every device. We can't turn into every device. Sometimes it's just not possible. So the next then condition, how do we turn the other condition? We'll get rid of the other condition, for example, non-preempt. Now let's look at the circular weight. The circular weight usually happens because process number one, and we have two processes, and they want to do some work, and both of them, they need two resources. Just an example. Resource number one and resource number two. They both need, for example, this is a file and this is a printer. Each process wants to open the file, read some information and send it to the printer. So if they go in and this process takes this resource and this process gets this resource, and then this one wants this resource, remember if it's pointing at it, that means I want it. If the arrow goes from the resource to the process, that means, what does it mean? Allocated. So if the way you read it, you always look, where's the tail of the arrow you start? You say resource number two is allocated to process two. If the arrow goes from the process to the resource, how do we read it? How do you read this arrow? Request. Process number two is requesting resource one. So you need to read the name of the process and the name of the resource, or the name of the resource and the name of the process. Anyway, so process number two has this resource allocated to it, but it needs that one. That one is not free. It's allocated to process one. So it has to go in a wait. So it goes waiting until this one is free. That means it's waiting for process one to finish and release this one. But process number one, in order to finish, it needs two resources. It has this one, but it needs that one. It requests that one. But that resource number two is not free, and therefore it cannot have it. So it goes in a waiting for it. So this one is waiting on this one to finish, to release this, but this one will never finish because it's waiting on this one to finish. They're both waiting on each other to finish. It's like a chef, two people who wants to go and cook some meal, and they both need two tools. Imagine if this tool was the frying pan, and this tool was the spatula. This tool was the frying pan, and that's the tool, the spatula. So now each person here needs the frying pan as the spatula, but this person gets the frying pan, this one has to wait on it. But anyway, so that's what a circular weight is. So this is the circular weight. And that's a deadlock. Because it has all the conditions. These tools cannot be shared. And this one that has the frying pan will not release it, so it's hold on weight and non-preemptive, and we end up having a circular weight. And once we have circular weight, that's a deadlock. So how do we prevent the circular weight? One suggestion is to have all the resources, have them in an order. Resource 1, resource 2, resource 3, resource 4. Have them in one list. And make this protocol. Tell everybody, if you want any 2 or 3 or 4, any group of these resources, don't get them randomly. Get them according to this list, the order of this list. So if you need resource 1 and 2, you must go for number 1 first. Don't go for number 2. If you have 1, then go for number 2. So this is the how to prevent a circular weight condition, how to remove it from a system. Does that work? Well, let's see if it works. So what we do, these two processes come at the same time. They both want this frying pan and this spatula. This guy goes for the frying pan, gets it? No, they're not allowed to go. This is, let's say this is a frying pan, and this is the spatula is number 3. Wow. Doesn't matter which one it is. So both of them, they must go for the top resource here. They cannot go for the spatula, they must go for the frying pan. So all this is done. So this guy, both of them arrive here, process 1, process 2. Whoever arrives 1/1,000,000 of a second before the other one will get the frying pan. Okay, so let's say process 1 got the frying pan. That's it. This one now is given to process 1, not process number 2. What happens to process number 2? It has to wait. Process 2 cannot go and get the other resource. Now, process 1 got this resource, it can now go to and get the other resource. And therefore, we will not have a deadlock. We will not have a circular wait if we can remove this condition. So there are always ideas of how to prevent that, but maybe we cannot always do it. If it can be done, it's brilliant. It's not a big deal. It's easy to implement in coding. So you give them an order and say, these are the resources. If you want any number of resources, you must get the first resource according to the list. Put them in the same order. Go. If you want resource 1, 3, and 4, don't go for 4 or 3. Go for 1 first. If you get 1, go for 3. If it's free, take it and go for 4. If not, wait until you get it. Now, the next condition. Hold and wait. We can stop, hold and wait as well. Anybody has any idea how stop and hold and wait? Or non-preemption? Right. This one says, when you start first, let's say we have these two processes, process 1 and process 2, and they need 3 or 4 resources each. Sometimes they're the same resources. Sometimes this one might need resource 1, resource 3 and 4. This one might need resource 1, resource 2, and resource 5. And maybe resource 4 as well. So if we say, there's another technique, say, okay, every process, declare all the resources you need. Everything you need at the start. And before we allow you to start running, we'll get you all the resources. If they're not available, you have to wait right at the start. So these two processes are right. Process 1 says, I need 3 resources. Say one of them is available, and 2, but not the 3 of them, then wait. So it goes right at the start. The other process also, we say, you need those, they're not available. Now, resource 1, 3, and 4 are available. We give them to process 1. So here are all the resources you need. So because this process got all the resources it needs, it will never have to wait. It never have to wait on anybody. It will start running. Whenever it needs resource 1, it has it. Whenever it needs, let's say it wants to read from a file, and it needs from some other communication line, it wants to print to the printer at the end. So it has everything. It never has to stop. This guy comes in and says, I need those resources. Sorry, resource 1 is with this process. It's not available. You have to wait. So process 2 is waiting. When this one finishes, it will release all its resources. And if they make up, if this one, they all become available for process 2, we give everything to process 2. It's like you want to draw a diagram. You need a ruler, you need maybe a calculator, you need a pen. If the 3 of them are available, you give them to you. You'll finish your diagram sooner or later. If they're not available, say no, you have to wait until the 3 are available. We cannot take a pen or a ruler from someone else, and therefore we remove non-preemption. And we also, this way, we stopped hold and wait. There's no hold and wait. We give you all the resources. You're not going to have 2 resources and then later on say, I need another one, it's not available. Go waiting while holding the first 2. No, we give you everything at the start. So this idea of anybody who needs any process that comes in, let's see how many resources do you need, tell us all the resources, and wait. You can't start until we give you all the resources in one go and you can continue. Okay, so you need to understand these ideas and you need to be able to answer. If we want to remove this condition, mutual exclusion, what should we use? So anybody remembers? Do you remember how do we remove mutual exclusion? Using spooling, right? And also you need to be able to explain spooling. So this one is solved by spooling. Any devices that are shareable or non-shareable, dedicated devices, we run spooling and they become virtual devices that appear to be shareable. Thank you. And then if we want to stop circular weight, how do we stop circular weight? By having a list, an ordered list of all the resources. This is just the idea, it gives you the key word, ordered list. List all the resources in one list. Ordered list of all resources. Okay, you need to finish the rest of it, how to explain. And then any process that needs any number of resources has to go to that list and pick them in the same order as the list. You can't go to pick a resource from the bottom of the list before the one at the top of the list. That will make sure we'll never have circular weight. How do we prevent non-preemption or hold and wait? By giving all the resources that a process needs are right at the start, if they're available. Then it never has to wait, or it never has to go in a wait and hold another resource. So it stops both. Is that clear enough? All right. What we're supposed to be talking about as well. Now we're going to be just talking about recovering from a deadlock. To recover from a deadlock, if there are 3 or 4 processes and you need to recover from them, the easiest way that you probably have already done many times, if your kind of laptop just got frozen, you say, oh, my laptop froze or got locked. It could be a deadlock. So there are few processes that are deadlocked. Of course, there could be 10 or 12 processes running, but 3 of them, especially the one you're reading, is not coming back to you. Word is not, you keep hitting all keys, Word is locked. With another process, you don't know which other process. So a lot of the times what you may have done is press the restart button. You cut down power, kill all the processes that are running, and start again and run them again. So that's one solution. It works, but it's a very expensive solution. Because if you have 50 processes running, and then you switch them all off, that's a lot of work that was done by many of the other processes that's wasted. And they have to do the work again. And sometimes if they have to do the work again, they could generate a lot of problems for you. Let's say, if you say, I'm going to double the working hours for all the staff, for example. Every staff member, we have 1,000 members of workers, and everybody who worked for 10 hours, you're going to give them 20 hours. Everybody, we're going to double. So you read the record, multiply into 2, save it, you do 5,000 of them. And then somebody powers down the power. The whole thing collapses. Power is off, the process is killed. Now you run it again later on. You add another 10,000 to the same group. Now you've added them, instead of 10%, 20%. Well, that's wrong. So there could be a lot of problems if you stop a program from running or a process and then run it again. Unless it's just a process that just displays information, it doesn't change information or data on the hard disk or on the files or on the database. Right, so one way to solve or get out of a deadlock situation is to turn all the processes, kill all the processes. That's of course a very bad, inefficient way of doing it. The better way is to identify, if you have a program that does the deadlock detection, the one we use the diagram, as we looked at the diagram, and if we can find out which processes are deadlocked, out of the 50, there could be only 3 that are deadlocked, and just terminate those 3 processes. Kill the processes that are involved in the deadlock, that are deadlocked. So if that works, it will definitely free them again and start running them again. But again, those processes, one of them could be updating a file. It's really bad. If you're updating a file, you've been doing it for a minute or so, or you've updated 10,000 records, now you run it again, it's going to update the same 10,000 records again before it gets to the next one. So again, the best way is not to kill all the processes, not to kill the processes that are involved in the deadlock, but to only kill one of the processes. So first, identify which processes are deadlocked. Let's say you find 5 processes deadlocked, or 3, or whatever. Let's have an example. Here are a few processes that are deadlocked. Process 1 needs a resource. That's already with the process number 2. That needs a resource. That's already with process number 3. That needs another resource. That's already with process 4. And process number 4 needs a resource. That's already with process number 1. So as you can see here, circular weight, process 1, 2, 3, and 4. There are 4 processes deadlocked. Of course, this may already have a few other resources. There might be 2 other resources that are available, resource 7 and resource 9. This one might have one other resource, resource number, 3 is already with this process, but it needs another resource here, which is maybe resource number 1, and so on. So there are many other resources, 2, resource maybe 7, 8, 9, and so on. So some processes are waiting, or they are in a deadlock, but they have more resources, 4 or 5 resources. So now, which process do you think we should pick of those? These processes that are all deadlocked, which one do you think we should, who is the victim here? So really, our job here is just to pick the victim that's going to be terminated. So which process do you think you should be picking in general? 3. In this particular example, 3, process 3, where is it? This one here. Why? Any idea why? Anybody has any suggestions? Remember, what we want to do is minimize the damage, minimize the waste of work that was done, minimize any problems. Any ideas? Come on, guys. Okay, let me suggest one thing. If this process has 5 resources, no, where is the process? There it is. Process 3 has 5 other resources. It has 5 other resources holding and waiting on just this resource. If it gets this resource finished. And this process has 2 resources. This process only has 1, and it needs another one. Which process will you do? The one that has more resources, if we terminate it, remember, if we terminate any process, these resources will become free. They might be helpful for another process, whoever needs them. So the process with more resources, if you terminate it, it will release more resources. And that will have a better chance. Of course, the most important thing, if this process is terminated, that resource becomes free. And that will be taken by the process before. But also these 4 resources, they might be needed by another process. Okay, so like, for example, this could be a color printer, and this is also a color printer. Or this one here needs color printer. So by terminating this one, it releases this resource that can be used by this, but has also released a color printer that this guy doesn't have to wait on that one. It can use this color printer. So in general, the process that's deadlocked and is holding more resources, that's probably a good idea to terminate it first. It might solve. You might only have to terminate this process, and that will release this resource that will be used by this one. And when this one finishes, it will release this resource, and this resource now can be used by that, and that can be enough to break the deadlock, the circular deadlock, and every process will finish. Maybe. But this process could have been running for the last 10 minutes. You know, 10 minutes in CPU time, 10 minutes must have done billions of instructions, a lot of work. While this process just started. It only worked for 1 second or half or 1/100th of a second. It hasn't really done much work. So let's pick the one that hasn't done much work, because if it runs again, it's going to run. That one hasn't wasted a lot of time. Remember, anything done in the past is wasted if you terminate it. It has to run it again. And if this one has been running 10 minutes is like 10 years in our time. 10 minutes at CPU time. It must have done a huge amount of work. So it's a good idea to terminate the processes that have just started running, rather than the ones that have been running for a long time, just to save that CPU energy that was all used to run the process. And another thing, if this process, for example, we say, okay, well then let's terminate this process, but this process is updating files. It has been writing to files. That's dangerous. Never ever terminate a process that writes information to databases, and then you say, I'll run it again, because it will write again to those files. And if it's adding values, it will add the values twice, and that can be wrong. It's like to say, okay, I'm going to run a program, it's going to tell us how much money we send in tax to the government. So you say it's all 20%. So 20% send, and then you run it again, you send to the government against 20%. So you do it twice. Now that's dangerous. The one that writes information to files should never, any process that updates files, do not terminate it. That's a general recommendation. All right, anything else? Any other suggestions? There's something called priority. Does that ring a bell? So these processes may have different priorities. Which process would you pick based on priority to terminate? The lowest. Go for if they have priority, go for the lowest priority, the least important job. Because least important job, most of the time, it does nothing. It displays few images or pictures or plays some music or something or whatever it is. It's not a very highly prioritized kind of job. So this is the way to recover from a deadlock. There's no easy and a good way to recover from a deadlock. Usually it happens by turning off the machine, killing all the processes and start again. But that's not an efficient way. We can reduce the number of processes to terminate by just picking the processes that are deadlocked. And here in this case there are 4 of them. Terminate those 4. But that's not good either. The better way, identify those processes that are deadlocked and pick one of them. And you can give maybe recommendations of which one to terminate. Let's start again. Which process would you terminate in order to recover from a deadlock? The one with the least priority. Give me another choice, another recommendation. Somebody asks you, which process shall we terminate? What would you tell them? Other than the priority. Anybody? Yeah?
Which have more resources allocated.
Pardon?
Which have more resources. The process which have more resources.
The process that is holding right now, waiting, and is holding a lot more resources. As in this example here, process number 3 is waiting on resource 9, but has 4 other resources holding on to them. If you terminate this one, these resources will be released. Of course, it wants number 9, it's holding number 2. So it will release number 2, but it will also release all the other resources that might you have a better chance of terminating the deadlock by making more resources available. Any other recommendations? The one that holds more resources, the one that has the lowest priority. Anything else? Anybody wants to listen to me? No, thank you. Give the others a chance. Well, she's absent for 3 days or 3 weeks, and then she comes 1 week and she wants to make her imprint on that. Yeah.
Don't terminate the process that is writing information or reading.
Do not terminate a process that is updating files. That's writing to files on your database. That's dangerous. Do not terminate. Terminate simple processes, but maybe that print reports, generate reports. Because even if you terminate it and run it 5 minutes later, the report is going to be even more up to date. All right? And that kind of finishes our deadlock topic.